Welcome back. In this video we're going to talk about the dot product and its use in constructing orthogonal projections. One of the major ideas behind the projection definition is that in some cases when you have two vectors you want to find components of one vector in the direction of another vector. So let's suppose we have two vectors, x and y, and we'll put them in Rn, where for Math 1C we say n is 2 or 3, but it could be anywhere up to any natural number, which is pretty amazing. What if, oh God, of course I meant what? What? What if we wanted to construct orthogonal vectors P and R such that we could write y as the sum of these vectors P plus R where P is in the direction of x and R is orthogonal to x. Okay, that's a bunch of words. Blah, 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 blah. What the heck does that just mean? I mean, I might as well have spoken in the same language my 15-month-old son speaks in, right? A better way to say this is the following. You can copy that down in your notes because what we wrote up here is what we're going to draw down in this diagram. So we have, let's suppose we had two vectors that are not directly in the same direction. They're not exactly in the same line. So we're making an assumption that I can't write x exactly in the same direction as y and vice versa. And I'm going to actually make this an obtuse angle. It doesn't have to be, but it kind of is a fun mechanism. We call this angle between the two of these things theta, if you remember. Sometimes we will want to construct a way to project y onto the direction of x. Remember, the direction of x is the set of all scalar multiples of x. So we're going to go ahead and draw that direction right here. So the dotted line right here represents the direction of x. This line is the direction of x. And we define this line. This is quite an interesting way to define it. We define this line as the set of all scalars alpha times x, where alpha is in R. So literally the way that we get that line is just multiply x by every single possible scalar. In this whole idea, when we have these two vectors, the idea of an orthogonal projection is to say, can I construct a creative way to get this vector right here, and I'm going to call that vector P, so that when I take y minus P, so I take P, subtract that away from y, I get back to a vector called R, which is directly orthogonal to x. You see, and you could also draw, if you wanted to, we'll call this vector R. This is going to be known later in your life as the residual vector. And then this will be the projection. So this, what we're going to call this the projection. Well, what is a projection of? It's the projection of y onto x, right? Because if you look at what we're doing here, we're constructing this projection, right? So that's the question. Can you orthogonally decompose y as a vector in the direction of x and then a vector directly orthogonal, such that when you add these two vectors together, do you see it? If I add p and then go up r, I get directly back to x. Okay. So let's go ahead and figure out whether or not this is possible. To construct such a projection, we want to find, because that's what WTF means, right? Want to find. We want to find a scalar alpha such that P is equal to some unknown scalar. We don't know what the scalar is going to be, but we know that whatever it is, alpha times x should be equal to p, since p was in the direction of x, right? So that was the construction. We were going to do this by trying to find that alpha. That's the real choice, right? So this is some unknown alpha times x. To do this orthogonally, to do this so that P is an orthogonal projection, we need to consider the residual vector. And we called that residual vector R. And we said that R came from taking our original vector y and subtracting p from it. That goes back to this diagram, right? We had our original vector y, we subtract p from it, and we get r. But if we assumed that p was alpha times x, well, this is just alpha, unknown alpha. We're still searching for that, right? The fact that this is orthogonal, the fact that we're looking for an orthogonal projections, means that if we look at the relationship between x and r, we want this dot product to be equal to 0. This is from the fact that the dot product between two vectors is 0 if and only if these vectors have a 90-degree angle, and we call that orthogonal. Okay. Well, we know from the algebra of dot products that R was chosen to be the difference between y and p. And then we can use linearity in the right argument to say that the relationship must hold something like this. Well, I also just used homogeneity of the dot product, so I distributed and then I brought out the alpha. Alpha is the unknown. Each of these are now scalars. This goes back to your history in elementary algebra. I have two scalars and one unknown. What do? Yeah, isolate the variable on one side. So this would be x dot x. So I brought this over to the other side. And now I've got this is x dot y. And then finally I can write alpha as x dot y over x dot x. This is the amount of x that I need to go to get directly perpendicular to y. So when I look at this scalar alpha is the exact amount to apply to x and get directly under y. And let's talk about what that intuitive statement means. Again, remember, the whole idea of projections is to orthogonally decompose one vector in the direction of the other vector. So here's our x vector. We wanted to know how much of x, what scalar do I have to multiply by x to get directly under y. So this projection right here was perpendicular. And then once we had that perpendicular projection, we could subtract that thing and get the vector r. And we use some interesting algebra to actually say that the amount of x that we need is given by the scalar alpha that we've just constructed. And I write it in blue because now I know what alpha is. It's the dot product between x and y divided by x dot x. And we can go further here. So now we're going to call P is going to be the projection. Again, it's the projection of y onto x. Okay, and we just said that this is going to be alpha times x. And I'm going to write this over here because I really want to focus on this alpha. So here I've got x dot y over x dot x. This is now a scalar. Notice this is a scalar because the top is a scalar, the bottom is a scalar. And then this is scalar vector multiplication because I'm multiplying alpha times x. Okay. On the bottom, notice that x dot x is the 2 norm of x squared. So now we've got this is x dot y over the 2 norm of x squared. And then I'm going to take this scalar multiple and multiply it by this vector. And then I'm going to do something even further. Here, there are 2 copies of the 2 norm. So I'm going to leave one copy directly under the dot product. I'm going to leave another copy, reassociate that copy, because this multiplication is associative, right? And now this is the unit vector in the direction of x. Notice, since this is a unit vector, this whole vector has magnitude 1, which implies that the magnitude of the 2 norm, well, remember, the magnitude of the projection, this is going to be the magnitude of alpha times x okay, which we just said was going to be equal to the magnitude of this whole vector. So now this is xy over the 2 norm of x times x over the 2 norm of x. Okay, do you see it? So all we did is just a little bit of algebra to translate. We just did that algebra up here. This thing, again, this is a scalar. Do you see this scalar? So we know that when we take a scalar out of the norm, all we have to do is slap an absolute value on that scalar. And then we can leave the vector inside the norm. But we just said that this vector has length 1. So that goes away. And then here, when we take the absolute value, the denominator of that absolute value is going to be always positive. So I can apply the absolute value only to the numerator. And what we see is this is now the length of my projection. So we called P the projection of y onto x. Because this is so famous, we're going to give a new definition. This is going to be known as the scalar component of y in the direction of x. And it is this scalar. It is the scalar x dot y over the 2 norm of x. And it tells you the exact amount of the unit vector in the direction of x that you would need to scale by in order to get directly under y so that the residual vector was orthogonal. In the next video, we'll take a look at an example of how this works in practice. See you there.